This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on a fascinating paper detailing a reinforcement learning approach to satellite orbital path planning. The authors propose using an advantage actor-critic A2C agent, leveraging two-line element TLE data for a more realistic simulation. What immediately strikes you as significant about this approach, given the complexities of orbital mechanics and the existing methods?
The most significant aspect is the use of reinforcement learning, RL, specifically A2C, to tackle a traditionally challenging optimization problem. Traditional methods often rely on computationally expensive techniques or heuristic approaches that struggle with real-time constraints and dynamic environments. RL offers the potential for adaptability and scalability, crucial in the increasingly congested low Earth orbit, LEO. The use of TLE data adds a layer of realism, grounding the simulation in actual satellite data.
The paper highlights A2C's superior performance compared to proximal policy optimization, PPO. Can you elaborate on the reasons behind this observed advantage in this specific context?
A2C's superior performance stems from its ability to handle the exploration-exploitation trade-off more effectively in this physics-constrained environment. PPO, with its trust region approach, can be overly cautious, limiting exploration and potentially hindering the discovery of optimal yet unconventional orbital configurations. ATC's unconstrained policy updates allow for more aggressive exploration, leading to faster convergence to high-reward solutions. The use of vectorized parallel environments in ATC further enhances exploration by simultaneously sampling diverse orbital scenarios.
The paper emphasizes the importance of a well-designed reward function. How does the reward function in this work balance competing objectives like target coverage, safety, and altitude constraints?
The reward function is a weighted sum of sub-rewards, each addressing a specific objective. Ground target validity is rewarded exponentially, incentivizing precise coverage. Orbital safety is incorporated using a hyperbolic tangent function, smoothly rewarding safe distances. Altitude constraints are handled through a normalized error term, penalizing deviations from the desired range. The weights can be adjusted to prioritize different objectives based on mission requirements. Furthermore, soft constraints on eccentricity and inclination are included to promote stable and predictable orbits.
The custom simulation environment built on OpenAI Gymnasium plays a crucial role. How does the use of TLE data enhance the realism and practical applicability of this environment?
TLE data provides realistic initial orbital parameters, ensuring that the training starts from plausible configurations. While TLEs only reflect the instantaneous position, the simulation focuses on the overall orbital configuration, reducing the need for continuous updates. This approach balances realism with computational efficiency, making the environment suitable for real-time applications. The use of TLE data also allows for easy adaptation to different satellites and mission scenarios.
The paper mentions a custom callback for handling learning plateaus. Can you explain the mechanism and its importance in this specific RL application?
The custom callback monitors the agent's performance and detects plateaus in the learning curve. When a plateau is detected, the callback forcibly resets the orbital configurations, forcing the agent to explore different regions of the state space. This prevents premature convergence to suboptimal solutions, a common issue in RL, especially in complex environments like orbital mechanics. The callback also includes periodic evaluations to ensure that the intervention is based on actual policy quality, not just noisy rollouts.
The architecture of the policy and value networks is described. What design choices were made, and why were they considered beneficial for this specific task?
The policy and value networks are both fully connected, feed-forward neural networks with 3 hidden layers using leaky ReLU activation. Leaky ReLU was chosen over ReLU to mitigate the dying neuroth problem and avoid vanishing gradients, ensuring consistent weight updates. The architecture's depth allows for capturing complex relationships between orbital parameters and rewards. The actor network outputs the mean and log standard deviation of a multivariate Gaussian distribution, enabling stochastic action selection and exploration.
The paper presents a detailed comparison of A2C and PPO. Beyond the cumulative reward and time steps, what other qualitative differences in the learning dynamics were observed?
Beyond the quantitative metrics, A2C demonstrated a more consistent and stable learning curve. PPO's learning curve showed more oscillations, reflecting its more cautious exploration strategy. A2C's parallel environment setup allowed for faster propagation of successful strategies across different agents, leading to quicker conversions. The visualizations of policy and value function losses further support this observation, showing faster convergence for A2C.
The paper concludes by highlighting the potential of reinforcement learning for scalable and intelligent LEO mission planning. What are some of the limitations of this approach and potential avenues for future research?
While this work demonstrates significant promise, there are limitations. The accuracy of the simulation depends on the accuracy of the TLE data and the Keplerian model used. Real-world orbital dynamics are more complex and include perturbations not fully captured in this simplified model. Future research could incorporate more realistic models, including atmospheric drag, solar radiation pressure, and gravitational perturbations from other celestial bodies. Furthermore, integrating collision avoidance algorithms and considering more complex mission objectives would enhance the practical applicability of this approach.
The paper mentions the use of state-dependent exploration, SDE. How does this technique contribute to the overall robustness and efficiency of the training process?
SDE introduces stochasticity into the action selection process, allowing the agent to explore a wider range of orbital configurations. This is particularly beneficial in environments with sparse rewards, where deterministic exploration might get stuck in local optima. By adding noise to the actions, SDE encourages the agent to explore regions of the state space that might otherwise be overlooked, leading to more robust and efficient learning. The combination of SDE with the custom callback further enhances exploration and prevents premature convergence.
The hyperparameters for both A2C and PPO are listed. How are these values determined, and what is the significance of their tuning in achieving the reported results?
The hyperparameters were tuned through experimentation, balancing exploration and exploitation. Key parameters like learning rate, entropy coefficient, and value function coefficient were adjusted to optimize the learning process. The choice of these values significantly impacts the convergence speed and stability of the RL algorithms. The use of techniques like gradient clipping and advantage normalization further contributes to stable training. The specific values reported represent a balance between exploration, stability, and convergence speed optimized for this particular task.
The paper uses a multi-input policy in Stable Baselines 3. What are the advantages of using this type of policy over a simpler, single-input policy?
The multi-input policy is crucial because the observation space is a dictionary containing both continuous orbital elements and discrete binary flags for target validity, safety, etc. values. A single input policy would require flattening this dictionary, potentially losing valuable information about the structure of the observation space. The multi-input policy allows the network to process these different input types separately and then combine their representations, leading to a more informative and effective policy. This approach is particularly beneficial when dealing with heterogeneous data, as is the case in this orbital mechanics problem.
The paper mentions the use of VEC normalize. What is the purpose of this wrapper, and how does it improve the training stability?
VEC normalize is a wrapper that normalizes the observations and rewards across multiple parallel environments. This is crucial for improving training stability because it reduces the scale mismatch between different inputs and rewards. Without normalization, the learning process can be dominated by features with larger scales, hindering the learning of other important features. VEC normalize ensures that all inputs and rewards are on a similar scale, leading to more robust and efficient learning. This is particularly important in this application where the scales of different orbital parameters and reward components can vary significantly.
The paper focuses on LEO. How adaptable is this framework to other orbital regimes such as medium Earth orbit, MEO, or geostationary orbit, GEO?
The adaptability depends on how easily the environment can be modified to reflect the specific characteristics of different orbital regimes. The key changes would involve adjusting the bounds of the action space, orbital elements, and the reward function to reflect the different constraints and objectives of MEO or GEO missions. The underlying RL algorithm, A2C, and the network architecture are relatively general and should be adaptable. However, the specific hyperparameters might require retuning for optimal performance in different orbital regimes. The TLE data would also need to be sourced appropriately for the target orbit.
The discussion of the clipped surrogate aggressive in PPO is interesting. How does this mechanism contribute to the stability of PPO compared to other policy gradient methods like TRPO?
The clipped surrogate objective in PPO is a key innovation that improves its stability compared to TRPO. TRPO uses a trust region constraint based on KL divergence to ensure that policy updates remain within a safe region. This constraint can be computationally expensive and limit exploration. PPO's clipped objective function provides a similar effect but without the explicit KL constraint. By clipping the importance ratio, PPO prevents large policy updates that could destabilize the learning process. This makes PPO more sample efficient and easier to implement than TRPO.
The paper highlights the importance of aggressive exploration for optimal convergence in this problem. How does the choice of A2C and its implementation facilitate this aggressive exploration?
A2C's inherent design facilitates aggressive exploration in several ways. First, its unconstrained policy updates allow for larger steps in the policy space, enabling the agent to quickly explore different regions of the state space. Second, the use of parallel environments allows for simultaneous exploration of multiple orbital configurations, increasing the chances of discovering high-reward states. Third, the synchronous update mechanism ensures that all agents learn from the same policy, leading to faster propagation of successful strategies. This combination of factors allows A2C to effectively balance exploration and exploitation, leading to faster convergence to optimal solutions.
The paper mentions the use of a moving window for plateau detection in the custom callback. What is the rationale behind using a moving window instead of simply comparing the current reward to the previous reward?
Using a moving window for plateau detection adds robustness to the system. Comparing only the current reward to the previous reward can be sensitive to noise and fluctuations in the learning curve. A moving window averages the reward over a certain number of steps, smoothing out these fluctuations and providing a more reliable indication of whether the learning process has stalled. The size of the moving window, patience parameter, is a hyperparameter that can be tuned to balance sensitivity and robustness. A larger window is less sensitive to short-term fluctuations but might miss smaller plateaus.
The normalization of the reward function is mentioned several times. Why is this normalization crucial for stable training, especially in the context of this complex reward structure?
Normalizing the reward function is crucial for stable training because it prevents numerical instability and ensures smooth convergence. The reward function in this work is a weighted sum of several subrewards, each with its own scale and range. Without normalization, the learning process could be dominated by subrewards with larger scales, hindering the learning of other important components. Normalization ensures that all subrewards contribute equally to the overall reward signal, leading to more balanced and stable learning. Clipping the final reward further enhances stability by preventing outliers from disproportionately affecting the learning process.
The paper provides specific values for the hyperparameters. How sensitive are the results to changes in these hyperparameters? What would be the impact of, say, doubling or halving the learning rate?
The sensitivity to hyperparameter changes varies. The learning rate is particularly sensitive. Doubling the learning rate could lead to unstable training, with the agent oscillating wildly and failing to converge. Halving the learning rate might slow down the convergence process significantly, potentially requiring much longer training times. Other hyperparameters, such as the entropy coefficient and value function coefficient, also have an impact, but their sensitivity might be less pronounced. Systematic hyperparameter tuning is crucial to find the optimal values for a given task and environment. Techniques like Bayesian optimization can be used to efficiently explore the hyperparameter space.
The paper focuses on optimizing 5 Keplerian elements. Could this framework be extended to include other orbital parameters or consider more complex constraints such as fuel consumption or thruster limitations?
Yes, the framework can be extended to include other orbital parameters or constraints. Adding parameters like true anomaly, though it's instantaneous position, not a fixed characteristic, would require modifications to the action and observation spaces. Incorporating fuel consumption or thruster limitations would necessitate changes to the reward function, potentially adding penalty terms for excessive fuel usage or thruster firings. The complexity of the reward function and the network architecture might need adjustments to handle these additional factors. However, the underlying RL frame is flexible enough to accommodate these extensions.
This has been a very insightful discussion on the application of reinforcement learning to satellite orbital path planning. Thank you for your expertise.